Alright, exercise 6.9. So basically we want to determine the stiffness matrix for a particular mesh size, and we're going to use sort of the typical mesh size that you start with is just a uniform one. So how do we get the stiffness matrix? Basically we take our hat functions phi j from j equals 1 to m. So by the way, we are what are we doing here? So, yeah, we've got this interval from 0 to 1, and 0 happens to be x0, and 1 happens to be xm minus 1, and then we have x1 all the way up through xm, and these will be like here, and then you've got, of course, some stuff in between there. So basically we've got, let's see here, m plus 1 plus 1, so we've got m plus 2 distinct points in the interval from 0 to 1. One of those is x0, which is 0. One of them is xm minus 1, which is 1. And so the uniform mesh size is going to be, h is going to be, you take 1 and you divide by, well, for each of these gaps between an x0 and an xi, basically between each xi and xi plus 1 there's an interval there which will be of length h. And so if we think of how many intervals there are m minus 1 of them, because that's one less than the number of boundary values that we have. Well, you take the number of total points you have and you subtract 1, and then you get the total number of gaps that you have there. And so, yeah, to get h in this scenario, it would just be equal to 1 over the quantity m plus 1. But actually writing it in terms of m is not important. But it is important to know, like, to keep track of our indices so that we can actually form our matrix. So if we look at the hat functions, or not so much the hat functions, we've already computed everything we need about the hat functions in the chapter. We computed that HII is just, you take HI inverse plus HI plus 1 inverse, and that holds for I between 1 and m. So this is an m by m matrix here. And so let's see. Yeah, because you've got you've got m hat functions. So because you've got m plus 2 points, each hat function is sort of defined by, you can sort of think of it as like the center of the hat. So like, for example, like if you've got, here, I'll draw it somewhere else. So you've got xi minus 1, xi, and xi plus 1 as your points. Then the hat function will look like this. This will be phi I. So you see that its peak is at xi, and then it just goes down and it hits 0 at xi minus 1 and xi plus 1. Therefore, in order to get your basis here, you only consider the middle values, and so you go from 1 to m, and so there's m of them. So yeah, that's why this is an m by m matrix, because each aij is given by, let's see here, aij is equal to the integral of phi j prime phi I prime dx, I believe, and this is of course from 0 to 1. I guess, in this scenario, doesn't matter. In our particular scenario, it doesn't matter. The phi j phi I is the same as phi I phi j. That might be more general. I don't recall off the top of my head. Anyways, so yeah, so we've got these formulas, AII. If you compute this directly, well, you could do that just looking at the hat functions and looking at their slopes and plugging them into the integral. And you'll get the AII is HI inverse plus HI plus 1 inverse, and then AI I plus 1. So like, for example, that would be like, if I is 1, then you have 1, 2. So like this value here, that would be just negative 1 over HI plus 1. So this would be negative 1 over, and then h2. Okay, so now what? So in that particular example, since all of the intervals have the same length h, it's just minus 1 over h here. So we have this minus 1 over h out front, and then you've got that negative 1 there. Okay, so there's that. Also, a is symmetric, and so hi plus 1I is the same thing, because you just flip them. And so, yeah, so then if you plug in hi equals h for every single index I, you just get aii is 2 over h, and aii plus 1 is the same as ai plus 1I, which is negative 1 over h. And so you get this matrix. And yeah, that's about it. So this is basically like, I don't know, like can you plug in h into an equation and solve it? So I don't know, with a lot of these problems, like they seem really straightforward, so I sort of worry a little bit about like maybe I'm completely missing the point of these problems because they seem like they shouldn't be as easy as they are. Am I recording right now? Oh, I'm recording on my screen. I don't think I'm recording on my mic thing. Okay, so what that means is that the audio quality in this video, which I'm sure you've noticed, is awful. Just because I'm not going to go back and redo everything here. But yeah, anyways, so yeah, I don't know why this problem is a thing, but it is. And so, yeah, this is how you do the problem. And yeah, then you're, well, I mean, yeah, there is possible that it isn't. It's always possible in math that you're missing something, and the thing that you're missing is like the real like heart of whatever you're trying to understand. So there's always that risk involved there. But if this is how you're supposed to do the problem, then it's pretty straightforward. You just plug in different values of h for the hi and hi plus 1, and then you look at your matrix. Although the other neat thing to realize about this is that if you build a finite difference method to solve the Poisson equation, just second derivative of u equals f, if you just use this using like a finite difference method like you'd read about in Lebec, like in the second chapter, then you just make a matrix A that represents your approximation, and the typical like second order approximation matrix A is like this same thing, but you're dividing by h squared instead of h. And so this should sort of like remind you of that, and you should sort of think like, oh, maybe there's a connection here, and there most definitely is. The other thing, the h, I think that there is actually another h here, but it's on the other side, because like if you look at that, it's like ax equals b, and like this is what we've been talking about in this section of the chapter. You've got ax equals b, you've got a matrix A, and then you've got some matrix B as well, and B is also given by some integral formula. That integral will actually give you another factor of h. So you could, if you wanted to, take those h's and bring them over to the other side, and then you'd get a 1 over h squared instead of 1 over h here, and then it'd look very much like the finite difference method. But yeah, so that's about it for this section. Sorry about the sound quality, but hopefully this like makes it clear how this problem works.